Welcome everyone to a new edition of the Topological Complexity Seminar. Today, I want to warmly thank Professor Clara Löh from the University of Regensburg for having accepted our invitation to talk about her work on bounding LS category invariants via equivariant methods. Bitte, Clara.
Yeah, thank you very much. Thank you for the kind invitation and for having me here. Yeah, so I'll talk about lower multiplicity bounds, and I'll use classifying spaces to do that. So basically everything is based on joint work with various people. So it's Pietro Capovilla, Kevin Lee, Marco Moraschini, and Roman Sauer, and Kevin is also here. So yeah, I come from I don't know where, geometric topology maybe. My favorite invariants are superficial volume and bounded cohomology, and so I might have a different take on things, but I will later explain how I got into this and how it happened. Yeah, so I want to talk about these multiplicity invariants or category invariants, and then I'll later turn to classifying spaces and how one could use them. So yeah, maybe one more comment. So on the top of the page, you see a URL, and from time to time, I will upload the PDF so that you can flip back pages if you want to check on something that happened earlier in the talk. Okay, yeah, so the first definition, probably most of you are familiar with that, or at least a version of this. It's a version of the Lusternik Schnirelmann category, but we have additional pi1 constraints. So in the most general version, we could say, well, we have some class of groups F, we have some space, and then we want to define the F category of this space. So we first have to say what the allowed subsets are. And for me, these are subsets of the space that on the level of pi1 lie in this class F. So, well, of course, we have to be a tiny little bit careful about base points. So we require that for every base point, if you look at pi1 of your set and then you map it to pi1 of x via the inclusion map, that you end up in F. And then an F cover is just an open cover by such subsets. And the F category is the minimal number of sets in such a cover that you need to cover F, to cover X. And I'm yeah. Maybe for you this is a strange normalization, but I'm so used to it that I will stick with it. It's the number of sets in the cover and not the number of -1 in the set in this open cover. And yeah, moreover, so I usually think about this more in terms of multiplicity. So we can rewrite this. If we have a CW complex, then this is the same as looking at all F covers of X by connected sets, and then we look at the multiplicity, and this should be at most N, and that gives the same value. And of course, it can be infinite if your space is huge. Okay, so that's the invariant that I want to look at. And maybe we'll start doing some very basic examples or some basic observations. So maybe let's make this a remark. So there is a very simple class of groups to look at. So let 1 be the class of all trivial groups. And then, of course, this has been studied before, namely this then cat1. This was studied by Eilenberg and Ganea. And of course, we know that if X is a spherical CW complex, so its universal covering is contractible, then the 1 category of X, this is actually the same as the Lusternik Schnirelmann category of X. But in general, it might be different, right? The Lusternik Schnirelmann category is the Lusternik Schnirelmann condition is more restrictive. Okay, so that's one remark, and the other one is there is an obvious chain of inequalities. So if we have a class of groups that contains the trivial groups, and if X is a CW complex, then of course, what do we get? Yeah, well, we can look at the F category of our space. And then of course, this is bounded from above by the 1 category, because every one subset is an F subset, because trivial groups are an F. And of course, every Lusternik Schnirelmann cover is also 1 cover. So we get an upper bound in terms of the Lusternik Schnirelmann category. And the Lusternik Schnirelmann category can be bounded from above by the dimension of X plus 1, because this is now a W complex. So this doesn't make sense to do it like that. And for me, maybe the more interesting question is, yeah, what happens from below? So how can we get meaningful lower bounds for the F category of X? So that's the main question. And my favorite family of groups that I want to look at is the following. So especially for F being the class of amenable groups. And I'll explain this in a second. Okay, so yeah, I'll quickly explain what amenable groups are, and also why I'm interested in this case. But then most of the things that I will say later, they're very generic. It doesn't really depend on this family, except for the concrete things at the very end. So if you don't like amenable groups, then yeah, you can also forget about them to a certain extent. Okay, so yeah, let me give the definition of an amenable group. And I should say that amenability, this is more like a concept, not a definition. So there are many equivalent characterizations, and I'll just pick one that is easy to write down and that is also somewhat relevant in the applications that come later, but there are many other descriptions that are equally good in principle. Okay, so yeah, let me say when a group gamma is amenable, if what? Well, basically what we want is we want to have an averaging process for functions on gamma, and this should be invariant. Okay, so if there exists a gamma invariant mean on the bounded functions on gamma. Okay, I'll spell this out in more detail. So what does it mean? We want to have an R-linear functional. So we have an R-linear map M from these bounded functions, and then of course, as I said, it should be some kind of averaging process, so the result should be a real number. And now there are conditions. So of course, if we average over the constant function 1, then we want that the average is 1. We want to have positivity. So if we have a function that's pointwise non-negative, then also the average should be non-negative. So M of F is non-negative for all F bounded functions that satisfy F is non-negative. So this is pointwise. And then, so far it's easy, right? I mean, so far you could you could just take evaluation, let's say at the neutral element. But what makes the method complicated is the invariance property. So we want that for all functions and for all group elements, we have that if we evaluate the mean on gamma times f, that we get the same as the mean on f. Okay, and of course, gamma times f is just defined by translation. So this is just the function that maps x to f of gamma minus 1 x. Okay, so that's the definition of an amenable group. It's just something that has an invariant averaging process. So I'll try to upload this page. Let's see whether the system is compliant. Okay. Good. Yeah, so that's the definition. Maybe that's not in itself very helpful. So I'll give you some important examples that you somehow get an impression of what this is supposed to be. So of course, all finite groups are amenable. Okay, so why is that true? Well, you can just literally average your functions over your finite group, and then all the properties are clearly satisfied. Yeah, from then on, it gets slightly more complicated, but if you know some functional analysis, then you will immediately see that abelian groups are amenable. And how do you do that? Well, it depends on how you think about this, but you could think about this invariance property as being a fixed point among normalized positive means. And then you can use the Markov-Kakutani fixed point theorem to prove that you indeed find such a fixed point, and such a fixed point then, of course, gives you an invariant mean. Okay, so that's good. And then there's some inheritance properties. So amenable groups, so this class AM is closed with respect to subgroups. Okay, I mean, you just sit down and do it. Quotients, the same, you can just write it down. And extensions. So you can extension and the kernel and the quotient are amenable, then also the extension group will be amenable. So this gives you a fairly large class of groups. So in particular, all virtually solvable groups are amenable. Yeah? Or yeah, to make it even more concrete now, if you maybe like want to go towards applications, I mean, we want to think about these amenable subsets of spaces. So if you have spaces like a torus or like a ring-shaped thing, of course, these things will have amenable fundamental groups, so they are all allowed in our amenable covers. And yeah, I don't know. I mean, what's the typical set of this thing is, of course, if you would have like independent rotations or something, then you could model this by a torus, and this would be considered a small set in this world. Okay, so let me give you an example of a group that is not amenable. So that's the free group. This is not amenable, so this is the prototypical example. And you might know that this is all related to the Banach-Tarski paradox as well. And of course, there are crazier groups that are also not amenable. But maybe let's not go into this. Maybe just as a fun fact. So there's a nice open problem. And this is whether Thompson's group F, whether this is amenable or not. Okay, nobody knows. And I think, yeah, I don't know whether there's a fashion nowadays that says something about whether it's supposed to be amenable or not. I think it's pretty much unclear, because like all the invariants and so on that we know, it's always like a corner case of these things. Okay, yeah, so maybe let's look at some examples of amenable category, right? Just to also try to get a feeling for this. So maybe let's look at sigma 2, right? The surface of genus 2. Okay, so yeah, what can we do? I mean, clearly, if you look at the amenable category of this surface, the surface has dimension 2, so the amenable category is at most 3, so that's okay. What about lower bounds? I mean, we also certainly know that pi1 of the surface is not amenable, so we will need at least 2 sets. So the amenable category should be at least 2, so it's 2 or 3. Okay. And another thing that we maybe could look at is let's do this the following. So let's take a wedge of 2 circles, and then let's take an n-fold Cartesian product. And well, if we look at this, so we have the amenable category of this. Well, it has dimension n, so it's should be at most n+1. Yeah, and then with the lower bound, okay, so again, pi1 of that, if n is not 0, okay, then it's not amenable because you have a free group here. So yeah, so it's at least 2, but somehow it's maybe not so clear where we will end up. So the question is, what are the exact values, right? And you will know at the end of the talk. I mean, so how to do that. Okay, so yeah, I'm interested in this invariant, and why I'm interested in that is this will become clear from the rather short list of known obstructions for the amenable category that also translate into lower bounds, right? So obstructions for the amenable category. And yeah, maybe this is not necessarily chronological order. This is maybe by generality. So there's a very general thing, and that is given by bounded cohomology and simplicial volume. And I'll explain this at the very end of the talk, how one can get this. And the first proof of this was by Gromov. And very quickly after, there was an alternative proof by Ivanov. Okay, and this is my main motivation, how I got into this, is because these, I mean, you would phrase it differently, right? You would say if you have a manifold and it has small amenable category, then the simplicial volume has to be 0, and these are some of the strongest vanishing results till now that I know. So that's how I got interested in these numbers. Okay, so then I'll again try to upload this page. And give you more examples of obstructions, but now we have to restrict the class of spaces. Now, so now, I mean, this first obstruction is really, this is for completely general spaces. There's no restriction on anything. And then the next thing is, well, you need a spherical spaces, so it's a statement about groups. So this is for spherical spaces. You can also take L2 numbers. And I think originally this also goes back to Gromov. And then there have been various extensions by Roman-Sauer. And then you could restrict even further. So now you could like say you have in a spherical space, and it's also supposed to be a closed manifold. So for a spherical oriented closed connected manifolds. And now there's a variety of things that work. So there's the rank gradient of the fundamental group. There is the cost of the fundamental group. And then if you have residually finite pi1, then also the log torsion growth of the homology. So I just log torsion homology growth. Yeah, so all of these, and you can prove it all at once using a special version of simplicial volume. So in this unified version, this goes back to joint work with Roman-Sauer and Marco Moraschini. But partial results have been known before. Okay. And then also you can play this game in more general settings. So you can also, for example, look at relative settings, and then in joint work with Kevin Lee and Marco Moraschini, we also have some results that go into this direction. But maybe let's not go into these details. So what I want to explain in the rest of the talk is a common strategy to do all of these things. Right? I mean, or to maybe I should not say all, like to do the first two. I mean, the third one, yeah, you can do it in a similar way, but not literally like this. So, yeah, the goal is now, maybe let's call this 1 and 2, is to give a unified strategy. 1 and 2. Okay, and yeah, the idea is not very complicated. Namely, it is to use classifying spaces. Okay, so I'll get to section 2. I want to explain how we can use classifying spaces to do this. Okay, in fact, there are 2 key ingredients, and I always say these are 2 irresistible forces in equivariant topology. So the ingredients that you need is, first you need to look at nerves. I mean, you have open covers, so I mean, yeah, you always have to be urged to look at the nerve. And the second one is to look at classifying spaces. Okay, so yeah, let me first start with the nerve part. So that's pretty simple, of course. Yeah, I think we mainly all know how to do this. So let's say U is an F cover of our connected CW complex X. And maybe let's say that this F cover is also connected in the sense that all the sets in U are connected. Okay, so it's a nice F cover of X. And then of course we can form the nerve. Let's call this N of U. Okay, and I assume that you all know this, but maybe I'll still draw the picture. So we have our open cover, right? So that's U. Okay, and then how do we get the nerve? So, well, for every element of this open cover, we take a point or vertex, I should say, and then we put a finite set of vertices into a joint simplex whenever the common intersection is non-empty. Okay, so each of them have pairwise intersection. That's non-trivial, and also these 3 on the left-hand side, they also have a common intersection, so we get a 2 simplex. So that's the nerve. Okay, but now we want to use this additional information that we have, because we do not just have an open cover, but we have these constraints on the fundamental group. And a good way of encoding this is to say, well, let's do everything on the universal cover and then see what happens, okay? So what we can do is we can replace our U, let's call this U tilde, and I'll call this the lifted cover. I'll say in a second what it is. Okay, because there are like two things that you could do. You could just say, oh, I have my sets in X. I just pull them back to the universal covering, but that's not such a good idea because you might have different components. So you take the connected components of that. So you lift your cover to X tilde, and then you take connected components. So this is again connected. Okay, so that's something you can do. And then, of course, again, you get a nerve. So n of U tilde. And yeah, so what's new about this nerve, or what's good about it, is that it has an obvious action by gamma, right? You can translate your things like your sets in the universal covering, and this will give you a simplicial action on this simplicial complex. Okay, so gamma now acts on this thing, and yeah, once a group is acting, you can ask all kinds of questions, and of course, one question that you can ask is like, what's the isotropy? And this is what it connects back down to the pi1 constraint on U, namely the isotropy of this action will be inside of F. So the isotropy, this is in F. And maybe I should have been a little bit careful. Maybe I should say that F is, let's say, closed under, I mean, this is a family of subgroups of gamma. So this should be closed under conjugation and subgroup to make things simple. Yeah. I mean, there are various versions of this, but that's maybe the most straightforward one. Okay. And okay, you see that the isotropy of this thing is in F, and then somehow we are in business, right? Now we encoded the thing downstairs into something equivariant upstairs. So what else do we have? Maybe there's one other thing that we should talk about, namely now this nerve is not completely unrelated to X, but of course we have the nerve map. So this is a map that goes from X to, let's say, the geometric realization of the nerve. Okay, let's call it nu. So how do you get it? Well, you just take a partition of unity of X that's subordinate to U, and then you just use this partition of unity to write down convex coordinates, and that's your map. And here you can arrange it in such a way that yeah, you get a map from X tilde to n of U tilde geometric realization, and now you can do this, let's call it nu tilde, in such a way that this is a gamma map. Okay, if you choose the right type of partition of unity, then this will be a gamma map. And what else do you know? Of course, what's very important about this nerve is the nerve, you can say something about dimension in relation to the multiplicity. And of course, the dimension of this nerve is the multiplicity of U minus 1. Okay, so I'll note this down in a second. Just upload the page. Okay, so this is what we also have. We have that the dimension n of U tilde is at most, or is, I mean, it's equal to the multiplicity. Well, I mean, it's obvious for U tilde, but then you figure out this is the same as the multiplicity of U minus 1. Okay, so now we have all the data, but we somehow wrapped it into a equivariant setting. Okay, so let me give maybe one example application of how one can use something like that. So let me mention the following proposition. It was together with Pietro Capovilla and Marco Muraschini. So yeah, so let X be a connected RCW complex as always. Yeah, gamma is the fundamental group of X. Oops. And yeah, let F be a subgroup family of gamma. In the sense above, it's closed under conjugation and undertaking subgroups. And then the statement is the following. So if the category of X with respect to this F is small, so let's say at most 2, then we can say something about gamma, and it's somehow it's pretty plausible, right? You have your space X, and you only have like if you have such an F cover that consists only of 2 things, yeah, then you only have these 2 types of things, and it's very plausible that then pi1, in this case gamma, should just be pi1 of a graph of groups where the vertex and edge stabilizers are in F. Okay, and that's the statement. So then gamma is the fundamental group of a graph of groups with vertex and edge stabilizers in F. Okay, so this gives some restriction on pi1. Okay, maybe I just say 2 words about the proof. Okay, so there are different ways of doing this. So one way would be just to, yeah, basically brute forcing it and forgetting about the theory and just say, oh, I have my open cover. Okay, then I look at a connected cover, and then I look at multiplicity. And then I just do something like Seifert and Van Kampen. I need a rather general version of that, and then I just go for it. And this works, but it's like technically maybe not so easy to figure out how to do this in detail. So what's easier is to look at these equivariant nerves. And if you have such a small cover, then the equivariant nerve will be one-dimensional. So look at n of u tilde, where u has multiplicity at most 2. Okay, so this is a one-dimensional complex, and because the universal covering has trivial first homology, then you can look at the spectral sequence and you realize, oh, this has to be a forest. Okay, and we already know that gamma acts on that, and we know something on the stabilizers. So you just pick one connected component of this forest. This is a tree. And yeah, then you have your group acting on this tree. The isotropy of these vertices and edges is in F. And then you just apply that rule. And then you're done. Okay, so that's a fairly, I think, easy proof that only uses standard tools. Okay, so this gives you some first, maybe restrictions on which spaces can have lower category. But of course, to be fair, in practice, it will be not so easy to check whether a group can be written as a fundamental group of a graph of groups with such vertex and edge stabilizers. Okay, so that was ingredient 1. Yeah, let's get to ingredient 2. These are the classifying spaces. And of course, again, somehow I have to take my family into account. And fortunately, there is a whole theory around this. So this is about classifying spaces for families of subgroups. So as before, let gamma be a group. And let F be a subgroup family of gamma. Okay, and now we want to say what classifying spaces for gamma with respect to this family. And of course, you have to be a tiny little bit careful, right? Because there will be different models. So in definition, let's be careful. And then later I will be a little bit sloppier. So a model of EF gamma, what is it? So, well, of course, the prototypical example in the end will be E gamma. So what kind of thing is it? Well, E gamma is something that has a gamma action. So this is a gamma CW complex. Let's call it E for now. And it has the universal property. And the universal property is as follows. So first of all, it should have something to do with F. So we require that all isotropy of E is in F. Okay. And then the other thing is that this gamma CW complex E is terminal in the gamma homotopy category of gamma CW complexes with isotropy in F. Okay. So let me make this explicit. So for all gamma CW complexes X with isotropy in F, there exists up to gamma homotopy exactly one gamma map from X to EF gamma. Okay, so this means that EF gamma is somehow terminal, and these maps that appear here, we will call them classifying maps. Okay, so that's the definition. I'll again upload this page. And then we maybe try to understand this a little bit better. So, okay, now I define this in terms of universal properties. So maybe I should first justify that this is a non-empty theory. So the theorem, of course, is that such models exist. Okay, whenever you have a group and you have such a subgroup family, then you will always find a model. And of course, by the universal property, it will be unique up to gamma homotopy equivalence. And maybe I'll make it, I'll give one or two more or less trivial examples. So the first one is if F is the family of the trivial subgroup inside of gamma, then of course, this thing just recovers the usual classifying spaces. Okay, so that's the first thing. And the other thing is, of course, if you go to the other extreme, if you take all subgroups of gamma, then the point is a model. So that's not very exciting. And now if you vary the family, then you can somehow interpolate between these two extremes. And I have to say that, like, there's a little warning. So in general, it's very hard to come up with nice models. Whatever nice means, yeah. Yeah, I mean, I think we are very much used to, oh, I have a group and then I want to look at a classifying space, and then, okay, if the situation is somewhat geometric, then I will find a really nice model for my classifying spaces. But if the family F is non-trivial, then this can be very tricky business. But the good thing is, for us, basically existence will be enough, like that we have such a universal object, and then how it looks concretely is not so important for the things that I want to do in the following. But I strongly believe that if you, for whatever reason, get a better understanding of these models of classifying spaces, if you find good models, then I think one should be able to obtain really strong results. But yeah, I wouldn't know how to construct nice models in nice situations. Okay, so yeah, also let me give you a first taste of why these classifying spaces can be useful for us. So this is again together with Pietro and Marco. So I'll first write down what I mean, and then I'll say more about it. So yeah, let X be a connected CW complex. And again, let gamma be the fundamental group of X, and F should be a subgroup family. Of gamma. Then the F category of X. Now we can describe this in terms of classifying spaces. Namely, this is the minimal number, okay, in N with the usual interpretation for infinity, such that, okay, so what's the thing that we can look at, right? I mean, so we are in the situation, we have our space X. Well, then we have the universal covering. This has a classifying map to EF gamma. And now we can wonder, like, how complicated is this classifying map, or where does it, like how much of the classifying space does it have to reach? And well, this we can somehow stratify by dimension of the skeleton. And the condition is that the classifying map, okay, so that's the map X tilde to EF gamma, is gamma homotopic to a map to, and now I put this in quotes, the K skeleton of EF gamma. Okay, so let me write this down. So, okay, whenever we have a model of EF gamma, then we can look at the K skeleton of this, and this, of course, oops, lies inside of our EF gamma. And then we can wonder whether this classifying map up to homotopy factors over the skeleton. And the smallest skeleton dimension is this K, and then the category -1 is this minimal K. And why did I put the K skeleton in quotes? Of course, because we have different models, but it works for every model, right? So you can shift quantifiers around. Okay, so what's the proof? Okay, so if you want to say that the F category is at most this minimal K, what you can just do, well, if you have such a factorization, then you just pull back like the open stars cover. Okay, now this is a very rough description. So you imagine you had a simplicial model, and then you really have literally an open stars cover. You can pull it back. Otherwise, you first replace your thing by something simplicial. And for the other direction, well, what can you do? Now you take some open cover, and then you look at your nerve of the lifted cover. Of course, then you have the nerve map. And of course, this equivariant nerve, it has the right type of isotropy, right? So it has a classifying map to EF gamma. And then just by some cellular approximation, it will factor through the K skeleton. So this is, yeah, let's say cellular approximation, like equivariant nerves and cellular approximation. And this is basically the proof. Okay, and of course, I assume that for many of you, this does not come as a big surprise, right? And it's also not supposed to be a big surprise. It's just maybe a nice general picture, because yeah, of course, something like this was already in Island Ghanea. So let me give a little bit of context. So in Island Ghanea, they have this in the case of the trivial family. And another thing that has like exactly like the same structure is the characterization of topological complexity of groups by Faber, Grant, Lupton, and Oprea. So let me just write this down. So you can characterize the topological complexity of B gamma. So this is about the spherical spaces -1 via the classifying map. And now what do you have to look at? You have to look at the classifying map for the product group 2. And now what you have to take as a family is the family of subgroups of gamma times gamma that's generated by the diagonal subgroups. So this is Faber, Grant, Lupton, and Oprea. Okay, so this is very much of the same shape. Okay. So the statement is the same, right? TC of B gamma -1 is the minimal K such that this classifying map factors over the K scatter. Okay, so that's the background that I wanted to give, and now I want to the remainder of the time I want to explain quickly how we can use classifying spaces to actually get lower bounds, but it's basically already all here, right? So we have the category of the F category of X. We can relate this somehow to these models of classifying spaces for this family F, and we know it's somehow related to the K skeleton. Now, if we have something that is sensitive to dimension, then we are in business. Okay, so yeah, let me try to formalize this a bit. So this is a strategy for lower bounds, and then in the end, if time permits, I will give at least one concrete case where this works. So our setup is as before. So X is a connected CW complex. Gamma is the fundamental group. F is a subgroup family of gamma. And maybe let's give a name to the category. So -1. So for the obvious reason. So let's say K is the category, F category of X -1, and let's assume it's finite because otherwise there is nothing to talk about. Okay, so yeah, and what else do we want to look at? So now I want to find obstructions for small values of this. So the setting that I want to use, I want to talk about functors, because then I can make use of the full power of all these maps that are floating around. So yeah, the basic idea is very simple. So let's say we have two functors, H and K, and it will become clear later why I want to have two and not only one. And these should be functors that go from, say, gamma CW complex to a category C, and it can be fairly general. There should be a zero object in here. That's something that we want because we want to talk about vanishing of things. Yeah? But I mean, so imagine, I don't know, a billion groups or vector spaces or whatever. Okay, and these functors should be contravariant. Okay, and these functors should be related. There should be a natural transformation going from H to K, and let's call this natural transformation T. And our goal is to find vanishing results for T. Right? So the goal is find conditions that ensure that Tx tilde, so now this goes from Hx tilde to Kx tilde, that this is 0. And we can talk about 0 because our target category has zeros. Okay, so that's what we want. Okay, and yeah, let me upload this, and then I'll basically put all the information that we have into a diagram. Okay, so let's just start very simple. So we consider the following. Okay, so what do we have? We have our x tilde, that's the thing that we're really interested in. And of course, x tilde is equal to x tilde. Okay, that's not very surprising. And now we insert all the maps that we have. So yeah, we have E gamma. And of course, we have a classifying map. Let's call it C. And from E gamma, of course, we also have a classifying map that goes to EF gamma. Okay, so far so simple. Then we assume that K is the category, F category of X minus 1. So maybe let's say that E is the K skeleton of EF gamma. Like we pick a model and then we take the K skeleton. Okay, and then we know by the proposition that we had before that we will be able to factor our classifying map from X tilde to EF gamma over this K skeleton E. Okay, and here we have just the inclusion. Okay, and this will commute up to gamma homotopy. And it didn't matter that we split up our classifying map into 2 steps because the universal property says it's all the same. Okay, good. So that's what we have. Now we have these 2 functors, H and K, so we are eager to apply them. Okay, so let's just apply them. So we have our H of X tilde. Now, of course, things are contravariant, so everything goes the other way around. Okay, and yeah, so that's the new diagram. And here we have, of course, again, the identity. Yeah, now maybe we should, yeah, and maybe I can also add our K and this natural transformation that we have right here. Okay, so we have K of X tilde. We have the natural transformation for X tilde. This is the thing that we are really, really interested in. That's the thing that we want to be 0 eventually. And then we have K of E. And of course, this also, we can just apply K to this map that we found here. And here we have the transformation for E. And this will commute because it's a natural transformation. Okay, now there's a, like, let's put a big if. Okay, now let's create a wish list. Okay, so the first wish that we have is that the diagram on the left-hand side, well, it would be silly if it wouldn't be commutative. So we want to have that the diagram on the left-hand side is commutative. So let's just require that H is gamma homotopy invariant. So if H is invariant on the gamma homotopy, okay, so that's fair, I think. And then, okay, now you can see what we want, right? In the end, maybe it would be nice if we could say, well, K of E, this could be 0, right? And then we would be saying, instead of taking Tx tilde here, we could like travel all the way around the diagram. But of course, here we would have to revert arrows. So it would be really nice if this were, these 2 things were isomorphisms, okay? So let's say one that H, like the H of the classifying map from H E gamma to H X tilde, this is an iso, right? I mean, we can dream of anything. Then let's be even bolder and say, well, for this particular family F that we are looking at, maybe we could even say that also the lower classifying map thing should be an iso. Okay, of course, I mean, in general, this is hard to satisfy, but if you have it, then everything is very good. Okay, and then the last thing is this thing over here. We could say, well, K of E should be trivial. So maybe we formulate this in a more general way, and then it looks friendlier. So let's say K of Y is 0 for all CW complexes Y whose dimension is small enough. So with dimension of Y less than the F category. Less than the F category of X. Okay, so okay, I wanted to also indicate where all of this happens. Okay, so if all of this is satisfied, so then this is an isomorphism, this is an isomorphism, this thing here commutes, this thing here over here is 0, and then we can really, instead of going directly, we can take this huge detour, right? Whoops, like that. Yeah, and then the thing will factor over 0. So then we really have what we want to have. Then T of X tilde has to be the 0 map. Okay. So if we're under these very fortunate circumstances, then we can get this. Okay. Okay, so far this is just wishful thinking. So I'm running out of time. So let me just give you the one example that I'm really interested in. Why can't I add a page? So that's weird. Oh, sorry. Here. Okay, sorry. Yeah. I'll quickly upload, and I'll be done in 3 minutes. Okay, so let me give you one example, but there are more. This is not the only one, but this is also one that explains why we want to have this very general setup. So, okay, of course, F is supposed to be the family of amenable subgroups of gamma, right? Okay, so what do we take as functors? As functors, we take for H, we take bounded cohomology with real coefficients. I can say in a second what it is. And as K, we just take usual cohomology with real coefficients. And then there is a natural transformation between them, and that's called the comparison map. Okay, so maybe I should say one word about what this is. So usual cohomology is singular cohomology with real coefficients. I should, okay. Yeah, I should be careful. Gamma, like everything, of course, in the gamma world, right? Sorry. Okay, it's the gamma version of this. And here the bounded cohomology is the same. You're looking at singular cochains, but they should be bounded with respect to the one norm on singular simplices. Okay, so there's a bounded version, but of course you can forget that things are bounded. So you get this comparison map between bounded cohomology and ordinary cohomology. Okay, so then let's look at our list of things that we have to satisfy. So 0, this gamma homotopy invariance, this is really not very difficult. 3 also clearly is satisfied because this is just ordinary cohomology, which also has a cellular description, so you're fine. And then 1 and 2, okay, they maybe are more like miracles in bounded cohomology. So these are non-trivial statements about bounded cohomology. So this is maybe the I'll put it under the term mapping theorem by Gromov. I can say one thing about it. So we have seen the definition of amenable groups, and the definition was there is an invariant mean. So you can imagine that, like in the same way that you can do transfer in ordinary cohomology with finite groups, in this bounded world on bounded cochains using this invariant mean, you can also do transfer with amenable stuff. And this works in a very, very high generality. So this will allow you to like kill all the higher homotopy groups basically because they're abelian when it's amenable. And it also allows you to get rid of the family of amenable subgroups in this classifying space business. I mean, this is very rough, but you should at least see what the vague connection is in this case. And well, if you all put this together, then you see, and sorry, I made another silly mistake. I mean, I should say this is, let's say now in dimension, I have to do this, of course, in the right dimension. So let's do this in dimension k+1, okay, or bigger. Okay, and yeah, so what we get is that the comparison map, now we can also push it down to the original space level on X. This is the comparison map, that this is 0. Right, this is what we get from this like general setup. And this has consequences. So for example, as a special case, we can now figure out that because the comparison map in degree 2 of the surface is known to be non-trivial. So this is a statement about hyperbolic geometry. So this proves that the amenable category of the surface of genus 2 has to be 3. It cannot be smaller than that. Okay, and yeah, another example is that if you take H and K equal to L2 cohomology, then you can figure out that you get vanishing results for L2 Betti numbers of spherical spaces. So that's the result that I also mentioned at the beginning. Yeah, and of course we are like curious to see how far we can push this. So we have a few other things in mind, but yeah, I guess there's much more to do. So maybe I'll close with the 2 open problems. Just so that we have also something for the future. The first one is, so we have seen this characterization of category and TC. So there is an obvious question around. So this is like, for which spaces can we say that the amenable category of the product is bounded from above by the topological complexity of X? So let's put it like that. So for which X do we have this? And in general, this is wide open. So I mean, it's known to hold in many cases, but yeah, I don't know whether one even should expect the general relation, because the diagonal family and this amenable family, they're very different. And maybe another thing that is bugging me for a very, very long time, and which was originally the starting point for the project with Pietro, was, is there a cup length estimate on bounded cohomology for the amenable category? I mean, of course, we have it for Lusternik Schnirelmann category and yeah, usual cohomology. And it's tempting to think that there should be something for bounded cohomology and amenable category, but the obvious thing does not work because we don't have excision for bounded cohomology. Okay, I'll stop here. I'm very sorry for going over time, and I'm happy to take questions.
Thank you very much, Clara. Thank you very much for a wonderful talk. So please, everybody, just unmute yourself and please ask questions to our speaker.
Clara, I just have one point. I don't know much about graphs of groups. So could you give me an example? For example, if cat one of X is in your notation 2, if and only if the fundamental group is free. And so if cat 1 of X is 2, then that means cat of X sub F is 2 for anything. And by your theorem, you would get a graph of groups. So what graph of groups do you get if the fundamental group is free?
Well, you literally get it in the way that you would expect, right? You take your open sets, and you can also take like the nerve downstairs, basically. I think you can write it like that. And you take your open sets and you look at the fundamental groups that you have for your open sets, and then for the intersections, yeah, you get the edges, and also you look at what happens on pi1. That's maybe like if you have a concrete cover and you want to see what the graph is. But like abstractly, the graph will just have, like if you have a one cover, it should have just ones everywhere. But then you get, of course, contributions to pi1 of the graph of groups, because you have the graph structure. So this is more something like a homotopy co-limit than a usual co-limit. I don't know, this was maybe not a helpful description. Like, yeah, I mean, you like for a graph of groups, like the pi1 of it is you get contributions by the vertex groups, and like they are related to the edge groups, but then also the graph structure plays a role. And whenever you see like loops in the graph, this will also generate stuff in the pi1 of your.
So if the group is free, though, is it simple?
Yeah, I mean, you would have, yeah, you would have like everywhere. I mean, you could build it by having everywhere trivial loops.
Yeah. Okay. Okay. I see.
That's one way to get it. I mean, there are different ways of getting it. It could arise in a more complicated way, but yeah. Yeah. So I mean, yeah. So maybe a good or one way that I like to think about these problems is, let's imagine you have the circle, right? And you want to compute pi1 of it. And then of course, like naively, you would say, oh, I cover my circle by two half circles that overlap, right? Then everything has trivial fundamental group that appears in this decomposition. Yeah, your two sets and the intersections. But there's non-trivial combinatorics going on, and this gives you the integers in the end.
I see. I see.
And this is like
Okay,
just big brother of that.
Mm-hmm.
Clara, I was wondering regarding your first open problem, if there is a concrete example of such a space X with this satisfying this inequality.
Oh, I mean, we do have examples for that. I don't know, like whenever X is classifying space of geometrically finite hyperbolic group, for example. I mean, we have many positive examples. We have no negative examples, but I mean, I would assume they exist. I mean, it's kind of weird that it should always be satisfied.
Well, are amenable groups closed under taking products?
Yes. I mean,
so that
amenable,
means,
yeah.
So that means if you had X with a fundamental group that's amenable, then that category is 1, right?
Yeah. Yeah, that's
and
always.
So, yeah, so TCX could be very big.
So you were asking about equality. Sorry, then what was the question?
I don't know, Jesus, what did you want? An example, satisfying or satisfying equality?
Just inequality.
Yeah, okay, so I mean, for inequality, amenable groups would be an example.
What if you, well, I'm not, I don't have a feeling about amenable groups, but if you change the family, would it be possible to get better lower bounds for TC?
Well, I mean, so if the family is the diagonal family, then you have equality for spherical spaces. But I mean, to me, for me, there's no obvious way to like mitigate between amenable groups and the diagonal family. So that's why I'm skeptic that it should be true in full generality. So yeah, but like amenable category, yeah, maybe it's yeah, it's not so easy to grasp. So I think the best way to understand it is through these results on bounded cohomology of simplicial volume and L2 numbers. This is the best thing that we currently have. We don't have any, or we don't have many other obstructions that work. So it's very hard to get a feeling for that. It's very complicated.
Well, I think this is a good place to stop the recording.